Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is class 4, and today we listen for a rhythm hidden inside all of matter. Here's a wonderful idea to sit with. Line up every element in order of atomic number and walk along that line. Properties do not wander randomly, they rise and fall and return, again and again, like a drum beat. Sarah once told me she used to memorize the periodic table as a giant chart of unrelated facts. Then she learned to read the rhythm instead. And suddenly, the whole table folded into one idea. Neat is happy if you can spot that rhythm. G wants more. It wants the reason humming underneath it, something called effective nuclear charge. Today, one idea at a time, we build both the rhythm and the reason. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the modern periodic law and why properties repeat, the 4 blocks S, P, D and F, the neighborhoods where elements live. Second, the grade size trends, how atomic radius and ionic radius change as you move across a period and down a group. Third, ionization enthalpy and electron gain enthalpy and the anomalies that break the smooth pattern. Fourth, electronegativity and the idea underneath every single one of these trends, effective nuclear charge, explained through Slater's rule. And fifth, the G drills, assertion and reason, mash the column, and order and exception questions, so that everything you learn today you can also score with. Ready? One idea at a time. Let us start with the law itself. The modern periodic law says something simple and profound. The properties of the elements are a periodic function of their atomic number. Arrange the elements by increasing atomic number, and their properties come back around at regular intervals. And here is the cause, the heart of it. That repetition happens because the outer shell electron arrangement repeats. Once asked why sodium behaves so much like lithium. The answer is that both end their configuration the same way. One lone electron in an outer S subshell. The table is built to show this pattern. Horizontal rows are periods, 7 of them. Vertical columns are groups, 18 of them, and elements sharing a group share their valence electrons, so they behave like chemical cousins. And finally, we divide the whole table into 4 blocks, named for the subshell being filled: the S block, the P block, the D block, and the F block. 4 blocks. One rhythm, running through every one of them. Look at this map carefully, because 2 directions unlock every trend in this chapter. Follow the amber arrow first. Moving across a period from left to right, the atomic radius shrinks. It feels backward, but here is why. Each step adds 1 proton to the nucleus and 1 electron to the very same shell, and shells shield each other polarly. So the pull on that shell only grows stronger. Chemists call this pull the effective nuclear charge, and across a period, it climbs sharply. Now follow the violet arrow. Moving down a group, the atomic radius grows. Each period downward adds an entirely new shell, farther from the nucleus, while the effective nuclear charge on the outer electron barely changes. Across shrinks, down grows. Now, the beautiful part, ionization enthalpy and electronegativity do the exact opposite of radius. They rise across a period and fall down a group, because both are really tracking that very same effective nuclear charge. And here is the G delta that lifts you past neat. Slater gave us a rule to estimate that pull. Effective nuclear charge equals the atomic number minus a shielding constant called S. Learn to reason with this rule, and you can defend every trend, not just recite it. Now let us look at size more closely, because ions behave differently from atoms. First, the trend we just met. Across a period the radius decreases, and down a group it increases. Same logic as the arrow map. So you already own this one. Second, when an atom loses an electron to become a positive ion, cation, it shrinks. A sodium ion is smaller than a sodium atom. With 1 electron gone, the same nucleus now pulls the remaining electrons in more tightly, and sometimes a whole outer shell disappears. Third, when an atom gains an electron to become a negative ion, an anion, it grows. A chloride ion is bigger than a chlorine atom. The extra electron adds repulsion and swells the cloud. And fourth, the trapped G loves isoelectronic species, ions with exactly the same number of electrons. Since the electrons are equal, whichever one has more protons pulls hardest and is smallest. Now among oxide, fluoride, sodium ion and magnesium ion, the order runs oxide biggest, then fluoride, then sodium ion, then magnesium ion smallest. More protons, smaller ion, sit with that carefully. Now to energy. How hard is it to remove an electron, and how much energy is released when one is gained? First, the first ionization enthalpy, the energy needed to pull the outermost electron away from a single neutral gaseous atom. The harder an atom clings, the higher this value climbs. Second, the trend. It rises across a period and falls down a group, the mirror of radius, because effective nuclear charge explains both directions at once. Third, successive ionization enthalpies always increase, and a huge jump appears the moment you try to break into a stable, noble gas core. A favorite clue for finding which group an element belongs to. Fourth, electron gain enthalpy, the energy released when a neutral gaseous atom accepts an electron. The halogens release the most, since they are just one electron short of a full shell. And fifth, the exception that only G really tests, no maybe bus or A, B enthalpy, is actually higher than aluminium's even though gallium sits one period below it. The reason, 10 filled d electrons sit in between and shield the nucleus poorly, so gallium's effective nuclear charge barely drops at all. Now the single most examined graph in this entire chapter. First ionization enthalpy across period 2, from lithium to neon. Watch the shape of the line closely. Overall, it climbs from left to right, exactly as we said. Lithium is low and easy to ionize, neon sits highest of all. But the climb is not smooth, and G adores the two dips inside it. The first dip runs from beryllium to boron. Beryllium has a neatly filled 2 subshell, but boron's outermost electron sits in a 2p subshell, a little higher in energy and easier to remove. So boron, despite having more protons, is actually easier to ionize. The second dip runs from nitrogen to oxygen. Nitrogen's half-filled p subshell is extra stable and reluctant to let go of an electron, while oxygen's extra electron is paired and feels repulsion, so it leaves more easily. Here's the delta that separates G from neat. This exact shape repeats one row down. Magnesium to aluminium is the very same subshell dip, and phosphorus to sulfur is the very same half-filled dip. Learn the pattern once, and you own both periods. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. The 2 ionization enthalpy dips, beryllium to boron and nitrogen to oxygen, repeat their exact logic 1 period down, and magnesium to aluminium and phosphorus to sulfur. Memorize the pattern, not just the period. 2. Electron gain enthalpy. Chlorine beats fluorine and sulfur beats oxygen, because the tiny period 2 atom is too crowded to welcome the incoming electron comfortably. 3. Every single trend you have met today traces back to one idea: effective nuclear charge, estimated by Slater's rule as the atomic number minus a shielding constant. A smaller, tighter atom simply holds its electrons harder. 4. Isoelectronic ranking and the diagonal relationship travel together. Lithium behaves like magnesium, beryllium like aluminium, boron like silicon, all for size and charge density reasons. 5. The exception only G tests. Gallium's ionization enthalpy is higher than aluminium's because filled d electrons shield the nucleus poorly and keep effective nuclear charge high. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one. Assertion: the first ionization enthalpy of boron is lower than that of beryllium. Reason: boron's outermost electron occupies a 2p subshell, higher in energy than beryllium's filled 2s. Think like Sarah. Check each statement on its own, then check the connection. Both are true, and the reason explains the assertion perfectly. Option A. Second one, assertion. The first ionization enthalpy of oxygen is lower than that of nitrogen. Reason, oxygen has a higher nuclear charge than nitrogen. Both statements are true, no doubt. But pause, does a higher nuclear charge explain a lower ionization enthalpy? No, that would predict the opposite. The real cause is nitrogen's half-filled stability, not oxygen's nuclear charge. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every single time. Third one, the G only exception. Assertion, the first ionization enthalpy of gallium is higher than that of aluminium. Reason, poor shielding by the intervening filled d electrons keeps effective nuclear charge high on gallium's valence electron. Check the reason first. True, 10 d electrons shield weakly. Now the assertion, with high effective nuclear charge, gallium clings to its electron just as tightly as aluminium, in fact slightly more tightly. Both true, and the reason explains the assertion. Option A. A quick match now. Say each answer aloud before I reveal it. Largest atomic radius, cesium, sitting at the very bottom left of the table, farthest from every nucleus's pull. Highest ionization enthalpy, helium, the smallest, tightest atom there is. Most negative electron gain enthalpy, chlorine, not fluorine, because fluorine is too small and clouded to welcome the electron as warmly. And highest electronegativity, fluorine, the single most electronegative element on the entire table. Lisa used to confuse fluorine's electronegativity crown with chlorine's electron gain crown. Two different elements, two different titles. If all four came to you before the reveal, effective nuclear charge is becoming your compass. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. Across a period, atomic radius decreases. Hold your verdict. Statement 2. Gallium has a lower first ionization enthalpy than aluminium. Think about shielding before you answer. Statement 3. Nitrogen has a higher first ionization enthalpy than oxygen. Remember the half-filled dip. Now, how many are correct? Two statements, the first and the third. Radius truly falls across a period, and nitrogen's half-filled stability truly does outrank oxygen. But the second one falls. Gallium's ionization enthalpy is actually higher than aluminium's. The exception poor shielding creates. Carry that exception into the exam hall. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. The two ionization enthalpy dips are a one-off, seen only in period 2. David believed this for months and stumbled the moment a period 3 question appeared. But here is the truth. The exact same subshell and half-fill logic repeats one row down, magnesium to aluminium and phosphorus to sulfur. Recognize the pattern, and period 3 stops feeling new. Myth 2. Down a group, ionization enthalpy always falls, with no exceptions at all. The truth. Gallium's ionization enthalpy is higher than aluminium's. 10 filled d electrons sit in between them and shield the nucleus poorly. So effective nuclear charge barely drops, and neither does the ionization enthalpy. Never trust a group trend blindly once d electrons enter the picture. Time to test yourself, rapid fire, and today it is all concepts, not calculation. Here is the rule. I ask, you answer in your head before the reveal, out loud if you can. Question 1. Which atom has the highest first ionization enthalpy on the entire table? Helium, the smallest, tightest atom there is. Question 2. In the series oxide, fluoride, sodium ion, magnesium ion, which is the smallest? Magnesium ion, the one with the most protons pulling on the same electron count. Question 3. Between gallium and aluminium, which has the higher first ionization enthalpy? Gallium, thanks to poor shielding by its filled d electrons. Question 4. Why exactly is boron's ionization enthalpy lower than beryllium's? Because boron's outer electron sits in a higher energy 2p subshell. And question 5. Which single element is the most electronegative on the whole periodic table? Fluorine. No exceptions, no arguments. If every answer came before the reveal, you have truly understood today's class. Let us gather the whole class in one slow breath. The modern periodic law. Properties repeat with increasing atomic number sorted into the s, p, d, and f blocks. Atomic radius shrinks across a period and grows down a group, and the real driver behind that, and every other trend, is effective nuclear charge, estimated by Slater's rule. Ionization enthalpy and electronegativity rise across a period and fall down a group, the mirror of radius. Through ionization, enthalpy dips, beryllium to boron and nitrogen to oxygen, and the very same pattern repeats at magnesium to aluminium and phosphorus to sulfur. Electron gain enthalpy favors chlorine over fluorine and sulfur over oxygen. And the G only exception, gallium's ionization enthalpy, exceeding aluminium's, comes from poor shielding by filled d electrons. And next class, we step into chemical bonding, Lewis structures, formal charge, and the V-separ shapes that decide how molecules actually look. And so, my friend, you have learned to read the periodic tables twice over, once for the rhythm and once for the reason humming underneath it. Every trend you will ever meet in JEE Chemistry, from bonding to acids to coordination compounds, quietly leans on the size and the effective nuclear charge you built today. Sarah, David, Lisa, and John all sat exactly where you are right now, learning the very same rhythm. Be patient with yourself. Revise the error map tonight, once, slowly. One idea at a time, you will crack JEE. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you inside a chemical bond.